And welcome back. Now, first of all, I wasn't going to do this video because it's a topic we've covered already in a couple of videos, I think, and it's all about pulse width modulation, PWM. But then I thought, hey, look, I'm actually implementing here what I've been telling you all about and how easy it is to do. So I thought, come on, let's video what I'm doing here. I'll try and keep it as short as possible, you know how it is. And I think you might find it quite interesting. There's a couple of little things in the coding, and there's a couple of little things here on the breadboard here. It's not complete by any means. I'm sort of in the middle of doing it. This bit here, for example, it's just all prepared bits and pieces. So let's first of all discuss exactly what this project's all about. Now, at work, I have a fan unit, a cooling fan, USB cooling fan. It looks remarkably like this one here. Let me just zoom back a little bit. There we are. See, now I've shown you this one before somewhere. It might even have been in that PWM video, I'm not sure, which is all very well and good, and it works nicely. Plug it into a 5-volt hub or something, but at normal power, it's just that tad too loud, just that enough to disturb you. And certainly here at home, it's quite irritating. Even though the sound isn't ginormous, it's just enough. So I thought, right, I need to create a very simple PWM control for that. And then something else happened. We had a cold spell here in the UK, and my mouse hand, as you can imagine, I've got my mouse and it's like this at work I'm talking about, and I sit next to a window, and the cold air coming down, even the double glazed window, hits my hand and eventually turns it blue. And it's extremely uncomfortable, as you can imagine. If I'm working about this, eventually the control in your fingers go and you can't type properly. So I thought, right, what do I need? And I needed one of these. Now, I'll wait until you've stopped laughing, okay, and we can continue with the video. This is what's known as a heated mouse house. You put your mouse in there. There's a heating element inside. This is a USB plug, as you can see here. It plugs into a USB port of some kind. And your mouse goes in there with this, of course. So you put your mouse in there. It's got a sort of a semi-rigid base, and your mouse is nice and warm. Well, your hand is nice and warm. Your mouse probably is as well. The heating element actually in here is tucked into the roof somewhere under here. I can just sort of feel it. Now, okay, yes, it looks a little bit, well, let's not go there. I'll just wait for you to stop sniggering at the back. Yeah, you, thank you. Yes, I've had enough comments at work about this. Yes, it is ginormous. It is a little bit unmanly, maybe. But the point is, it keeps my hand warm, all right? Except it keeps it more than warm. It's too damn hot in there sometimes. So whilst I'm not saying it's going to be a fire risk, it certainly is too much. And then I have to keep unplugging it at work. And what I don't want to do, of course, is go to a meeting or something, leave it on for 2 hours while it's getting hotter and hotter in there. Because, well, for all I know, my mouse might suffer a bit. Who knows? So with cruelty to animals in mind, what I needed was a pulse width modulator for this as well. So with the two things, it came to the fore like, right, I've really got to do this. So let's get on and do it. And I thought, right, how am I going to do this? I need 2 pulse width modulator controllers, but I certainly wasn't going to dedicate 2 nanos to the project. So I thought, hang on a minute, a nano's got enough pins. It should be able to do 2 pulse width modulated, different, separate, independent pulse width modulated outputs. Surely it can do that. Of course it can. And there's a couple of little niceties or gotchas, depending on which way you look at it, that I've discovered while I'm doing this. And I'm using pre-built USB sockets here. As you can see, this is let me just pan back a little bit. So this is a standard UK style double socket width. This is the thing you screw onto the wall, or indeed it could be inset into the wall. In fact, not this one. There are different versions of this that actually go into the wall, and then this screws flush with the wall, but I'm not doing that. I'm using this as effectively as a project box. And this one goes on here, and the USB things here come in these little snap-in modules. So this is a little snap-in module, okay, for a USB socket, because I wanted to plug them into USBs. I didn't want to cut the fan USB or the mouse house USB off, but I have cut these off. These actually came with the other end of this, which you might have spotted already over here for my testing, so it hasn't gone to waste. So I've got 2 of these, and I've got 2 spacers, but they're not going to be like that either. What I'm probably going to do is space these out a bit so that I have a socket, a spacer, the other socket will go in here, and in this one here I'm going to have to put a potentiometer, possibly this one here, or I have got another spare one somewhere floating about. Here it is. So I might put this one, you know, at the back of this one here. So that's my little pot control with a little knob, got loads of those. And then of course you think, well, how do we control that socket compared to the other socket? Let's put the other socket in so you get a full idea of what I'm doing here. Right, it's not in fully, but I'm not going to force it in. Well, we need a little switch, don't we? I was considering using the old touch thing again. I've used my fridge alarm and everything. That's very nice. But I just thought, well, a center off switch like this one here could be, well, just nice to use for a change, really. And it's easy to mount in this, isn't it? So this is a center off switch. And basically, all it's going to do, that's how it's going to be normally. So off, center off. But move it that way, and that one probably goes on, and move it the other way. A little bit fiddly, the other one goes on. All it's going to do is ground one of 2 pins on the nano to say I'm dealing with the mouse house or I'm dealing with the fan. And by using 2 pins like that, we can have them as input pull-ups, so they're normally high, but this will ground it, well, to ground. Okay, so and then it will know. And if neither's selected, so you've got center off, then the pot won't do anything. Doesn't matter where you set, because the code will say, well, you've not put to ground either of the pins, therefore logic says you're not actually trying to deal with anything. So we'll ignore that. Right, so that's the principle of it. I really wanted to get this done in about 3 days, but I've had it on my desk now for like 2 weeks already, because things happen during life, don't they? And they just, well, muck your plans up, really. So let me just draw you a quick schematic, really, about how this is going to work and the issues I've had. Well, I say issues, design considerations I've had to take when testing it out so far. Okay, and it's all gone according to plan, but there were a few issues on the output that I wasn't happy with, so I've had to make some changes. See, happens to the best of us, and especially me, of course. Right, so let me draw you a little diagram first, and then we'll come back to the issues. So the overall circuit's quite simple. You've got 2 MOSFETs being driven by separate PWM pins on different channels, and you've got a potentiometer that controls the speed of either one, and a switch that tells it which one of the ones it's going to control next. Simples. So let's consider some of the design aspects of this mini project, and let's face it, it's not going to be a difficult project, but it would be quite a nice project for a beginner. And I'm not suggesting that you have a mouse house heated or otherwise as part of your project, but you could control like the 2 fans or 2 motors. That's probably the most likely use, isn't it, in an Arduino world? 2 motors on a car, so you have a motor for the left wheel or a motor for the right wheel, and you supply power independently to those wheels. Will adjust both steering and power. Tanks and things and robots tend to do it that way, don't they? Because then you can spin. If you apply forward power on one, reverse power on another, you can actually spin the unit. Anyway, for me, I'm not spinning anything. I'm just heating up a mouse house and adjusting my fan. Let's connect this thing up. So I'll just show you it working first, and then we'll talk about the individual bit. Right, so it's all connected now, and as you can see, the fan, in fact, has started to go round. One of the design considerations or decisions I made anyway is that I didn't want the pot to turn this down to nothing. Now PWM, as you know, can vary between 0 and 255, so 0 means totally off and 255 means totally on, and anything in between, well, it's a fraction of the output. However, this fan will stall if it goes below a certain value, so I've designed it so that on minimum value, which it is now, it just about can go around, and in fact will start. Talking of going around and starting, you notice here, let's move these out of the way, it is in fact running on a 9-volt supply, and that's another design decision I've made. Yes, I've got the USB connected as well. That's just so we can see some feedback on the serial monitor. So it's working on a 9-volt, but of course this fan is 5-volt. Now I certainly wouldn't want to put 9 volts through it. Ditto for the heated mouse house, that is also 5 volts. So what did I have to do then to make it all work? Well, let's stick with the fan just for a minute, because you can see stuff on the fan, can't you, rather than the mouse house was all a bit hidden away. So I can turn this up and the fan will increase. So that's as maximum as I'll ever get, and that's really the annoying sound. You probably can't hear on the video that well. but it's blowing, and there's sort of a little bit of a shake on here as well. I guess the motor's probably well, barely 5 volts frankly, so it's working as hard as it can get. So if I turn it down a bit, there we are. Now the sound stops entirely, but I can still feel a nice breeze coming back from it, and I think that will be pretty good. Now the mouse house is also going to be run from here, but a different output. So let's talk about now the output stage and the things I've had to do. Obviously I've only got one output stage on here at the moment, but we can see what's happening. If we flip over just the code window just for a second, so what you're seeing here is the output from the fan, so this bit down the bottom. This first figure here displays what the input variable from this is, and analog inputs vary from 0 to 1023, but the output for a PWM varies from 0 to 255, so we have to map those values on. Now if I turn it up, you'll see them varying, look, up to 1023, 255. Now if I put it all the way down as far as I can get, the fan's 0, but the output is still 195. So it's quite a fine control I have on it, because I do want the fan to go round. I don't want it just, you know, either stalling or just going round at a few revs in a second. That just wouldn't give you any airflow whatsoever. Now the mouse mat though is different. So if we go in the code, we'll come back to the code in a little bit more detail. If we go down to the bit where it's getting this analog input from one of the analog ports, in fact I'm using A0, also known as pin 14. So we're reading it and saying, well, what am I actually mapping here? Is it a fan value or a mouse mat value? So the fan value will map the 0 to 1023 to 195, the lowest value. So I'll switch that down. You can see it is the lowest value, up to 255, which of course is the maximum value anyway. Fine. But for the mouse mat, I'm going to map it down to 50 and 255. To be quite honest, I should really map that lower. I should say the maximum is going to be 200 because it's actually too hot. But if you want it to heat up quickly, I might want to put it up to full power just for the first minute or so, and then pull it back down. Right, so that's how it maps the different outputs. But how do we then generate two outputs from the 1 nano? And the way we do that, we use a library again. Now we've used this library once before in the party strobe. Now for that I wanted to actually adjust the frequency of pulses, and I got it down to between 1 and 10 pulses a second, because that's about the range you want for a strobe. But here it's not the frequency I'm on about. In fact, if you look here, I'm setting the frequency on both pins here, 1 to 20,000, that's the fan, and the mouse mat to 1,000. We'll come on to that why in just a second. So it's not this I'm varying, it's the PWM output that I'm varying, but this gives us PWM on both ports, or 2 ports at least, and it's just a nice little library to use. And I thought, well, you can do it without a library as it happens, but then we're stuck with a different frequency of output. So I've dealt with this subject before, but this fan, I've held it up to the microphone just now, and of course all you could hear was the wind rushing. Well, I hope you heard that. If we change this, the Arduino default is something like 430 Hertz. One of the pins anyway is 430, another one is 900. Okay, well let's just, take 1,000 here. Let's assume that the fan pin frequency, that is how many times on and off a second it goes, was in fact the Arduino default-ish round about 1,000. Yeah, I know, Benny, it's not absolutely accurate, but we're just sort of rounding up, okay, if that's okay. He's a stickler for the detail, but we're going to use 1,000. He's not happy about 1,000. Yeah, I know, I should really look it up. All right, I'll look it up and tell them exactly what the frequency is, all right? So, as Benny insisted I told you exact figures. The frequency is 490 Hertz on the Uno. That's on most pins, and on pins 5 and 6 you get 980, which is close enough to the 1,000 that we're going to use here. So I'm going to upload this, and you'll see, well, hopefully you'll hear the difference and why I can't possibly use the standard frequency. It has a very annoying 1 kilohertz or 1000 hertz whine, and that would be absolutely unacceptable. I mean, here's me trying to get the sound of the actual fan blades a bit lower. I certainly don't want 1000 hertz whine while it's running. Hence the use of this library, so that I can up the frequency to something that I can't possibly hear. Now I could probably put it up to, I think 14,000 hertz is what I can just about hear in one ear. That's what happens when you get older. A child will hear stuff up to 20,000. So let's up that to 20,000 as it was, and hopefully that horrible whining noise will stop. So that's one good reason then for using the PWM library. The fact that I can set 2 different pins at 2 different frequencies, to me, is something that you might want in your particular project. We're not going to use anything on timer 0, any pin on timer 0. We're not even going to set anything. In fact, if you look at the code here, it says set pin frequency safe. Now what that means, don't fiddle with timer 0, because timer 0 is what's used in the Arduino world for delays and milliseconds counts and a few other things as well. So we don't want to mess about with timer 0 ever, but timer 2 and 3, or in this case 1 and 2, counting from 0, that's absolutely fine. So conceptually then, imagine this is your complete microcontroller. We'll pretend it's an Uno or a Nano because it just happens to be that family that has 3 timers. So in here somewhere you've got a bit of SRAM, you've got a bit of EEPROM, and of course you've got your actual microcontroller. Now within this you've also got 1, 2, 3 timers, which we've imaginatively entitled timer 0, timer 1, timer 2. Now the microcontroller, or at least the Arduino implementation of the software, talks to timer 0 to do things like delay and millis and stuff like that, right? So the microcontroller is talking to this bit of hardware and expecting things to work in here the way it was designed. If you start mucking about with timer 0, then you can you will certainly get problems with your delays and millis. They'll either be out or stop working altogether. But this is a separate piece of hardware embedded in that chip. Now you've got 2 more timers, you can see here, timer 1 and timer 2, and that's what I'm using in this project. By using the PWM library, I'm saying use the safe timers. That's this one and this one, not this one. This is not safe, as we've just discussed. So I'm doing things, or the PWM library is doing things to both T1 and T2, saying run faster, run slower, whatever. Well, I'm saying run at, one of them I'm running at, I think it's 20k hertz, wasn't it? And the other one at 1k hertz. And of course, nothing's happening to the microcontroller. It's not even using those. But what the library within it then is doing is talking to these timers, saying go and set this the way I do it, the mark space ratio, and these of course output their own independent PWM signal on the various digital pins. And the microcontroller, yes, it controls what's output on those pins, whether it's a digital output or PWM output from the timer. So it's not a direct output from the timer, it goes via the microcontroller, it switches things. But these are independent bits of hardware embedded in that little black chip, and that's why you can use them. And whatever happens to your microcontroller, no matter how busy that is, it doesn't affect what's going on in T1 and T2, which means they just run, well, forever. They won't stop outputting that pulse very, very accurately as well, I might add, because it's all separate hardware. That's exactly what we mean by the 3 independent, although contained, timers within an Uno or Nano. I'm using an eNum here. You might be going, an E what? I have used these before in some of my code, and it's just an easy way of having related variables contained within a sort of, well, container really. The eNum, which we're calling out type, starts at 0, the first one you declare, then goes to 1, then goes to 2 and 3 and 4 and 5, so forth. So you're saying, okay, so I've declared these 3 variables then, none, fan and mouse, within this out type eNum. How they're used? Well, basically you refer to those instead of the values. You don't ever say is it equal to 1 or 2 or anything else, you just refer to the name, so that if you had to change some values in here, you wouldn't have to go through your program changing all those values. Yes, you can do a similar sort of thing with the define, but this is just an example to show you how to use an enum. So if we look at the loop in here, what we're saying is, for example, here, look, current control equals out type : fan. For those of you who watched my video on library construction and class construction, you have to use that : It's just basically a C++ convention when you're referring to an owner of some kind. So out fan is the container up here, and these are all, well, members of that container. Right, so what we're saying in the loop is basically saying, has the value changed on the potentiometer down here for any of, for either the fan, if that's what we're working on, or the mouse mat? And if we're not working on either, we're going to return out of this loop. We're returning to the caller. Now, we're not made aware within the Arduino world is, well, what's calling this loop? In fact, what calls the setup? How does it all work? It's all a bit magic, isn't it? But take my word from it, there is in fact an outer shell program that says call the setup and then call the loop forever. I think the statement is while one loop, something like that. So that you can in fact do a return out of this loop back to the caller. Now of course it will send it straight back in again within a few microseconds, but that's fine. We just whiz round this until we've put that switch so that it's grounding one of the two pins, either the fan pin or the mouse mat pin, to say, ah yes, I do want to control that one now. At which point it then says, go and get me the value from the potentiometer, the mark space ratio. Has it changed? If it has changed, set the new value. We do a PWM write with the new mark space. Now I'm not happy with this code actually, because we're making a decision here on what type we're controlling. That is, are we controlling the fan or are we controlling the mouse house? And then we're saying go and get something, and then we're saying, are we controlling the fan? Otherwise do something else. That's clumsy code, but this is prototype code, so I'll tidy this up before I put it up onto YouTube for you to download. Here we've already looked at this briefly. This is saying go and get me the value from this pot and map it to an output value. Now this is a very useful little Arduino construct, the map. You give it the value that you've got. You say that value can vary between this one and this one, but I want those mapped to between this one and this one. So you don't have to do any convoluted, divisions and multiplies. You often see, if they want to do a straight conversion between an analog read and a PWM write, you'll obviously see a division by 4 with no remainder. But yeah, that works for the full range, but quite often you want to have a mapped range to pretend that this pot only changes the values here, for example, between 50 and 255 or 195 and 255. It just makes it a little bit more flexible. So that map command is jolly useful. The thing to remember about pulse width modulation is that once you've set it running on a pin, the actual hardware within this chip, this Atmel chip, for the PWM pin is sort of independent really of the main microcontroller. So no matter what you're doing, apart from resetting, I'd imagine, the PWM keeps going, which is exactly what we want, of course, isn't it? Right, let's think about then the tiny issue I had on the output stage, which is right down here somewhere. I went through various iterations. First of all, I used a transistor like this one here. This just happens to be a BC548, basically some standard NPN transistor. Now I have a little plug-in thing here that tells me the voltage and current. So it says the voltage now is 3.47. I'm using 260 milliamps, 0.26 of an amp. Well, that's considerably more than 100, which is why when I just put my finger down here to see if the transistor was getting hot and got quite a nasty burn actually. So serve me right, read the spec sheet before you start sticking transistors in. So what have I got here? Well, this is a standard gate level MOSFET. Now when I say gate level, 5 volt TTL. So let me just show you. Here's a bit of a drawing that I was doing while I was making it. So here's roughly, can't quite remember now, roughly the symbol for a MOSFET. The gate voltage in, drain goes to whatever power supply and the thing you're driving up here, and the source goes down to ground. Now you cannot use a MOSFET that is not TTL gate level, that is to say 5 volts, because if a standard MOSFET expects 10 volts here and you're only supplying a 5 volt pulse, what you're going to get across here is a very high resistance. Now this particular MOSFET happens to be this one here, which I've used before. It's an RFPI12N10L. It's a long name, isn't it? Anyway, this isn't a particularly low resistance MOSFET anyway. It's 0.2 ohms when fully on. So when it gets, say, a 5 volt pulse into that gate, the resistance across here drops to 0.2 ohms, which isn't bad, but these days you can get 0.02 ohms. However, that comes at a price. These were 10 for, can't remember, I know I bought them a pack of 10 though. It wasn't that expensive, but if you buy the really low ohm or low resistance ones, then they can cost you £1 a piece. Well, I'm not going to pay £1 a piece, so I didn't. So I'm using these ones, and I'll just make do with the fact they're 0.2 ohms resistance across the drain and source. And of course I'm going to need 2. So I've got one here at the moment working on the fan. I'll need to replicate this with the other pin out here. So this is currently connected to pin 9 because that's the fan output, and if I connect it to pin 3, that will be the mouse house output. So if you buy a standard MOSFET, it might seem to work, but you're getting a very high resistance because you're not driving the gate hard enough. It needs to be driven much more. The assembled board, it's all done now. This is the back plate, if you like, with its power supply. Power goes into this socket here, and yeah, I mean basically this is the voltage regulator down here. These are the 2 MOSFETs output. That's the pot. Well, that's about it really. So there we are. It's all done now. I think we'll go back up to the computer room and just discuss a few little things that I've done here, which may be of interest to you. And of course, we can see it working as well. So here we have on the bench here now the finished sort of project. I've just got to assemble it into the case here properly. But here we have the circuit board, the couple of MOSFET outputs, a variable, no it's not, it's a fixed linear voltage regulator, and the USB outputs, like I say. Now I've got a little power thing attached to one of them, but of course being pulse width modulated, it's not going to show the output unless I turn the thing up to full. So let's do that. If I turn this up to full using this little pot, I did decide by the way to use one of these. It wasn't the best implementation in the world, but well, you know, needs must. So that's up to full now. I don't know if you can hear this fan blasting away. It's doing really well. So on here we can see it's taking something like 340, 360. Well, that's the volts, which is a bit low, 5. 350, 340 milliamps, 0.4. Now I must say I'm a little bit disappointed. I'm not going to touch it because it's red hot. That voltage regulator there. Now if you remember the logic for using this voltage regulator, because well I didn't think the Arduino was going to cut the mustard to supply voltage to here, not the regulator on board. It can only deliver about 500 in total, and I didn't really want to stress this out either, because if this blew up, well then I'd have to replace the regulator on that. So I've put in this 7805 5 volt linear voltage regulator. It's only taking, as you can see down here now, look, 320, 340, something like that. But I daren't even touch this because it's so hot. If you notice, there's a nasty 3rd-degree burn on my thumb there where I touched it a few minutes ago. It's all gone red. It is hot, and I'm disappointed with that. I would have thought this voltage regulator would have managed, wow, at least 500 mil without getting that hot. I think they can go up to 800. But there we are. I might have to put a heatsink on this in due course, just a little tiny one bolted across there. We'll see. Right, so there's the switch. So what this does at the moment, because it's pointing downwards, it's controlling the fan. That is to say, it's telling the Arduino that we're controlling the fan with this potentiometer, which is upside down. So we're on full power at the moment, so I can turn that down, and you can probably see the fan in the background there slowing down. That's down to a sort of a trickle now, very nice too. If, however, I want to control the other USB port, this one here, remember both can be done simultaneously. That was another reason, of course, for getting that voltage regulator, so it can supply power to both. If I unplug it from here and plug it into this one instead, now that's actually going to control my mouse house, the furry little thing that is going to keep my hand warm, and it has been keeping my hand warm at work this week, except it gets a bit hot. Now, as you can see, nothing's happening at the moment because I'm too low. And in fact, we haven't switched over yet. So if I switch over, there we are. Now it's started that one up there, and it's taking whatever I put in here as the correct value. And you might be able to hear a whine because, well, I sort of deliberately set it down to, I think it was 1000 Hertz, which is still quite a bit higher than what the Arduino give you. Can you hear that? I can hear it very plainly. There's no way I could run a fan on that. I can run the mouse house on there because that won't vibrate, but the fan will. But it just shows you that, you know, it's all working as expected. That's full power. And if I flip it over again, so now I'm actually controlling the other port, which the fan would be plugged into normally, nothing I do here has any effect on that port there. Look, nothing at all. Brilliant. So it's all working. Now that's all well and good, and it's fairly standard, but there's a couple of little things that I made a design decision on whilst I was doing it, and it concerns the power and ground for both the switch and the pot. So let me just draw that out just to demonstrate that we can do this sort of thing, and why not. So what do I mean about using the Arduino as the power source? Well, imagine this. So this is our variable resistor. Now this is feeding in to the Arduino on, say, A0, right? So we're reading in a variable resistance, and we're expecting at this end to have 5 volts and at this end to be at ground. So obviously this goes up and down, gives us our 1024 steps and can be read in. Now the thing is, when I was building this, plus 5 volts and ground was a long way away from where I was actually putting it together. So I thought, well, hang on a minute, I'm at the Arduino here. I've got one of those 3-pin connectors. So why don't I just say, look, I'll deliver my 5 volts from a digital pin in the Arduino, and I'll deliver the ground from another pin. So effectively, that's what I've done. I've said to the Arduino, the power for the pot is now being provided by digital pin 8, and the ground is being provided by 7. What do I mean by this? Well, I'm setting this pin here to an output, and I'm setting it high, so obviously that's going to go to 5 volts. And for this one down the bottom, I'm setting this also to an output, but I want to make it go to ground, so I set it to low, which is ground low. That's effectively what a digital pin does. So by setting this one to low and that one to high, I'm supplying the 5 volts and ground that this potentiometer needs to read in the value. So that means I could put the 3 pins really close together. Well, it just happened to work like that on the layout. And that just about wraps it up. I mean, the project's built, it's in this box, it's going to be powered here from the 9 volts. As I say, I'm taking this into work tomorrow so that I can control my mouse pad and fan. So there we are, that's it. A couple of little things on PWM, just shows you can do a dual power. Hope I explained about the power, the timers on the power, and well, you never know. Every little nugget of information is useful to know, isn't it? Great stuff. Thanks for watching. Hope you enjoyed the video. See you in the next one. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.